We have two little fisherman sinkers that have been coated with plastic so that you're not touching the toxic lead of which they're made. And we're going to need the masses of these when we do the analysis of one of these oscillating at the end of a spring. So I have a scales here. I put a 20-gram weight on the pan, and I'll measure the first sinker, and it looks like it's 26 grams. So the first sinker is 26 grams, and now we'll try the other one, and it is also 26 grams. So now we have the masses of these two objects that we can hang from a spring. Next, we're going to measure the stiffness of this spring. It has a certain length now with nothing on it. We call that the relaxed length. If I place a sinker on the end of this and arrange that it's not bouncing up and down, here we see the mass hanging from the end of the spring. The momentum of the mass is not changing, so we know that the net force acting is 0. And then we will put a second sinker on the end and watch to see, and we'll measure the length of the spring when there are the two masses hanging from it, like that. So we're going to measure the relaxed length, the length with one mass, and the length with two masses. So here we go. First, we need the relaxed length of the spring, because the approximate force law for springs involves the stretch of the spring, that is, the length of the spring minus its relaxed length. So we need to know the relaxed length of the spring to analyze. And from the top of the spring to the bottom of the spring is 20 centimeters, 20.0 centimeters. So the relaxed length is 0.20 meters. That's the relaxed length. Now we'll hang one of these masses from the spring and make sure that it's not oscillating. And now we look at the length of the spring here in static equilibrium, and it looks like we have a length of 36.7. 36.7 centimeters is the 37. I should have said that better. 37.5 centimeters, or 0.375 meters, with one mass. Now we'll add another mass. And of course, now in static equilibrium, it stretches even more. And we now have a stretched length of 55.5 centimeters. That's 55.5 centimeters, or 0.555 meters. Let's repeat these measurements.
Say the thing about static equilibrium, because I said something wrong.
Okay. Here we have the relaxed length of the spring that we're going to need, because the spring force law involves the stretch, which is the length of the spring minus its relaxed length. The relaxed length of this spring is 20 centimeters, 0.20 meters. That's 0.20 meters. And now we'll hang one mass from that spring. And we'll arrange that it's not oscillating up and down. We see that its momentum is not changing, so the rate of change of the momentum is 0, and therefore the net force acting on the mass must be 0. From that we can conclude that the upward force by the spring and the downward force by the earth must be equal and opposite. Let's see what the length of the spring is. It is now 37 centimeters. 37 centimeters, or 0.37 meters. Now we'll hang the second mass, which should make it stretch even more. And again, we'll make sure that it just hangs there without oscillating up and down, so the momentum is not changing. The rate of change of the momentum is 0. The net force must be 0. Clearly, there's a bigger stretch of the spring, so a bigger net force upward by the spring, but also a bigger force downward because we've got the two masses. And now the length of the spring is 55.5 centimeters. 55.5 centimeters, or 0.555 meters. Next, we're going to take the hanging mass, stretch it a little bit, and observe its up and down oscillations. And we're going to time these oscillations to see how long they take. So it's important in doing this to start counting from 0. We're going to count 10 cycles, 10 complete cycles of the oscillation, counting from 0. So we go 0, 1, 2, 3, 4, for as many round trips as there are. And we will note in the records what the amplitude is. Now the amplitude is how far above and how far below the equilibrium position it goes. It corresponds to the amount of initial additional stretch from the equilibrium position. And we only need it approximately, but we do want to see what effect the size of the oscillation has on how much time it takes to make one oscillation. That time is called the period. So the approximate amplitude is half that total motion. So it's something like 5 centimeters amplitude. It's going down 5, up 5 for a total excursion of 10 centimeters. So with an amplitude of about 5 centimeters, we're going to time the oscillations. I have a stopwatch, and as it's heading down, I'll stay 0, and every time it heads down, I'll count again. So I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was 8.93 seconds for 10 cycles. 10 complete cycles was 8.93 seconds. Let's repeat this number. I go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.86 seconds for 10 cycles. Now let's do it with a larger amplitude. So we'll make it quite a larger amplitude. Let's say something like that, which is on the order of about 10 centimeters amplitude. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.75 seconds for 10 cycles. So we're again going to do this with a large amplitude. So I'll come down here with an amplitude of about 10 centimeters and let go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.70. Now let's do one other thing. Let's look at the oscillation for two masses on the end of the spring. And we'll do it with a small amplitude of 5 centimeters. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12.26 seconds. We should repeat this. Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12.23 seconds for 10 complete cycles.